we're going to take a look at how we can utilize MATLAB to be able to evaluate limits, but also how to verify those limits by using geometric approaches as well to kind of get like an eyeball or kind of a ballpark way of approximating, but then we can use MATLAB to get the analytic value. So let's say we have f as some sort of function, okay, or statement, and it's comprised of the symbolic variable x. All right, so we need a Sims function. Then we could use limit of f with respect to x as it approaches a. All right, or f in terms of x as x approaches the value a. All right, and that's going to find the limit. If we want to try to approximate or find the left and right hand limits, then we just use a fourth parameter, and we want to put that in the apostrophes. So we have apostrophe left and apostrophe right and apostrophe if we want the right or left hand limit. All right, so let's take a look at a really simplistic example. This x squared minus 9 over x minus 3 as x approaches 3. This one we could just factor, right? If we wanted to do a difference of squares, we could do x plus 3, x minus 3. The x minus 3s would cancel. We'd be left with x plus 3. Substitute the 3 in, 3 plus 3 is 6. So this one we could probably just do in our heads really easy. Let's use MATLAB to be able to verify that. All right, so first thing I'm going to do, I'm going to define two symbolic variables, f and x. I don't really need to define f, but I did anyway. Let's define f to be x squared minus 9 divided by x minus 3. All right, so that's our function. I'm going to suppress it. Now I'm going to take the limit as f is comprised of the variable x, and it approaches the value 3. And where am I getting 3 from? Well, back in the problem, it says x approaches 3. All right, so I'm going to go ahead and execute this. And remember, we did it in our heads and we got 6, and the answer is 6. So either I got really lucky and I guessed really well, or I knew what the answer was going to be. We could also do an easy plot of f. All right, and I'm going to turn the grid on. And we should be able to see that 6 is going to be the value that it approaches as x goes towards 3. All right, and lo and behold, as x approaches 3, which is right in here, then it looks like it's getting really close to 6. And in fact, you can see from the overlay. What I could really do is I could just change this from negative or from 2 to the bounds of 2.5, comma 3.5. Okay, if I really want to hone in on that graph. All right, and this could be helpful if for some reason MATLAB can't perform the operation analytically. All right, so here we go at 3, and it looks like it's measuring up to 6. And again, remember that unfortunately the function doesn't exist at 3. All right, so if you try to substitute 3 back in, you're not going to get a number, but the limit approaches 6 for this because we can factor. A couple more examples is the left and right-handed limits. So we have the absolute value of x divided by x, and we want to see the right and left-handed limits as it approaches 0. Before we do any of that, let's just easy plot this thing. All right, so I'm going to change this to the absolute value of x divided by x. And I'm going to say from negative 0.5 to positive 0.5. And I'm going to keep the grid on. And I'm going to turn this off. All right, and I'm going to suppress that. So let's just take a look at what the graph says before we do anything. All right, now notice from the left side, it looks like it's staying constant at -1. From the right side, it's staying constant at +1. And as we get to 0, well, we can't divide by 0, so there's nothing there. But it looks like the limit's approaching 2 different values. So we can take the limit as f is in terms of x as it approaches 0 from the right. All right, and if we execute that, the output is 1. All right, so the right-hand limit by looking at the graph is 1, which is substantiated by the graph as well as the analytic value. I'm going to copy and paste this, and I'm just going to change this to left, and it should be -1, right? If we're looking at the graph, clearly this is a value of -1. So I'm going to execute this. All right, and here's our -1. And if we look at the graph, again, substantiated right here. Now, I didn't ask you to do this, but what if I just went through and tried to find the limit as x approaches 0, not from the left or the right, and I run that? Well, now I get this NaN, and NaN means it doesn't exist. All right, and we could clearly see that from the graph as we approach the left and the right sides towards 0. Unfortunately, the function just does not have a limit as it approaches 0. All right, and that's why you get the NAN. Suppose we want to do an infinite limit, all right, or we want to try to find an infinite limit. And so we have one last example, and we have limit as x approaches infinity of x cubed minus 4 divided by x squared minus 3x cubed. All right, so I'm going to define my function f, and that's going to be x cubed minus 4 in the numerator divided by x squared minus 3x cubed in the denominator. All right, and I'm going to find the limit as x or f, which is in terms of x approaches INF. All right, so if you ever want to use infinity, INF is going to be the built-in function. And I'm just going to go ahead and execute this. I'm also going to do an easy plot of f. And let's just go ahead and do this from, let's say, -1,000 to +1,000, so we can see the long-term behavior on both the left and the right side. All right, so I'm going to go ahead and run this. We get -1/3 as our analytic value. And if we look at the graph, right, it looks like that we have a -0.3335, -3.333. So it looks like, yeah, it's trying to get to that -1/3 value, at least from the right side, right? Because remember, we said positive infinity. And of course, if I really wanted to, I could just make this from -100,000 to +100,000 and run it. And that's going to change the graph. All right. And we'd probably get a little bit closer to that 1/3 value. Right. Also, if I wanted negative infinity, all I have to do is just stick a negative in front of that, and I can execute it. And it looks like it's still becoming horizontally asymptotic at the same value of -1/3. All right. So pretty cool that now we can use MATLAB to evaluate limits. All right. Both left and right-handed limits, limits that exist at a specific point, infinite limits as well.